It's talking about arc lengths. We've talked about arc measurements as degrees. Okay, that was all in chapter 12. Now we're going to learn how to deal with it in terms of a length. Okay, and that's kind of why we did chapter 12 before we did chapter 10. Okay, we're also talking about areas of sectors, which is directly linked to areas of circles. Arc lengths are directly linked to circumference of circles. Okay, so if we can know what circumference and area of circles are, we should have no problem with arc lengths in areas of sectors. Okay. First thing we need to talk about is what circumference is. Not something you guys should be aware of since you all passed the 4th grade. Even though some of us took twice, right?
I didn't take kindergarten twice.
Oh my gosh, I'm listening.
I didn't take whatever grade twice.
All right, circumference. Circumference is the distance around a circle, right? It's an analogous kind of comparison to perimeter, but perimeters for polygons, circumferences for circles. Okay. Pi, where does pi come from? Pi, and that's spelled right, Pi. There is no E on it, okay? But that is the symbol for pi that we're going to use. You guys in the past have said, it's 22/7 or 3.14. Neither of those things are pi. Those things are approximations for pi. Does that make sense? Okay. We're going to use pi. We're going to use the symbol, okay, for the most part. A lot of your questions say leave it as an exact answer, or leave it in terms of pi. Meaning, do not use 3.14. Do not use the pi key on your calculator. Do not use 22/7. Use the symbol pi. Okay. But pi, what it is, and it's a physical thing that we cannot change. Okay. I think in the 80s there was a governor of Indiana. He just wanted to make it a law that pi was equivalent to 3. He wanted to change it. Can't do that. Okay. It's a physical relationship. Pi, every time that I take a circle's circumference, okay, and I have its exact circumference, which might be a difficult thing for us to do with our measuring tools. But if we have lasers, that's actually a pretty easy thing to do. Okay? We're going to take its circumference, and we're going to take its diameter. And if I divide a circle's circumference by its diameter, I will always get a quotient of pi. Okay? No matter how small your circle is, no matter how big your circle is, you will always get pi. Does that make sense? Okay? So I kind of show you that real quick with maybe a demonstration here in GeoGebra. All right, so it doesn't matter where my circle is, doesn't matter how big it is. So let's see here. All right, would you guys agree that red dotted line, no matter where I put it, is a diameter, right? Okay. If I ask for the circumference of this circle here, see if I can do this. I don't know if I can. Circumference of C gives me that number right there. Okay, so that's the circumference of this circle. When you see as I change the circle, obviously it changes, right? Okay, if I make A 1, okay, A is my radius, so I should get 2 pi times 1, and that's 2 pi, right? Does that make sense? 3.14, double that, you get that number right there. So that is the circumference, okay? if I take my circumference divided by my diameter, okay, circumference divided by my diameter, so my circumference was that B value, and I divide it by my diameter is this red distance, which is they're calling G. If I do that, hit enter, see how I get pi? Now, as I move those things, I don't know why, I guess it's just a fractional component that's going on there, but circle has to exist. You see there that it's either writing it as 3.14 or as pi as I start moving that through, right? The components that I use to divide are always different, but the quotient is always that number pi. Is that all right with everybody? All right. So that's a physical application, physical property that we cannot change. Okay. When we talk about the circumference of a circle, that's something you guys hopefully know by now. It's 2 pi r. Okay. Some of you know it. 2r is equivalent to diameter, right? Okay. So if you want to call it pi d, that's fine. You're going to see me call it 2 pi r just because of the nature of it. That's a more natural way of describing the circumference for some of the algebra and trigonometry that we do later in other courses. So 2 pi r is usually the formula for circumference that people will go by. Pi d is more like a formula that we use in the 7th grade, 8th grade. Okay. They are relatable. Okay, they say the same thing. Some questions that we're going to be asked are in regards to these two circles down at the bottom that share the same center. Okay. Those two circles are referred to as concentric circles. Okay. Concentric circles. Concentric just means they share the same center. Co together. Co means together. And centric means center, right? Okay, so circles that have the same center together or share the same center. Every piece of pipe that you look at, every garden hose that you look at is going to be a series of concentric circles, right? That makes sense? Okay. And you go to Lowe's or Menards or whatever, and you're trying to find pipe to fix a water break that you have at home or a gas leak or something like that. When you go and buy those things, you're going to see what they call an inside diameter, and you're going to see an outside diameter. Okay? If your pipes are going to fit together with the existing pipes in your house, you need to know which ones you need to buy. Do I need to buy the one that has an outside diameter of 3/4 or an inside diameter of 3/4? Does that kind of make sense? So that your pipes fit snugly together. That's a geometry concept, a geometry idea that a lot of people go to Lowe's and Menards and have no idea what they're doing because of the way things are advertised and marketed, which can cost you money if you don't pay attention to that kind of stuff. But it's concentric circle, and that inside diameter, outside diameter idea is going to come back to us at some point throughout the rest of the year. We'll do some story problems with it. This question here, this is relatable. It's the exact same concept as those of you that run track. Okay. Is there anybody in here that's in track, runs track, maybe watches track? Okay. Gage, you would probably watch track just like you watch baseball.
What do you ask? No, he didn't. He knows Gage plays the sport. I know he has some.
All right, so here's my track. Obviously, football field in the middle, right? Okay. When you guys are in an event, like if I'm running the 100 meters, we all start at the same spot. We all finish at the same spot, right? Okay. But when I run a 200, okay, so a 200 is going to start about maybe here and finish there. That'd be 200, right? Okay. We're all going to finish right here. Does that make sense? We're all going to finish at the same spot. But what do they do at the starting point for these people? Stagger them. Okay. And the people that are closest to the football field are furthest away, right? Or they stagger them kind of like this in their lanes. Is that right? Because the closer I am to the football field, I am running right here a smaller radius than the person out here is running. Does that make sense? Okay? So they have to stagger them so that everybody starts at the same spot. Okay? You guys okay? Oh.
You got a tissue or
It's just a spider, guys.
It could be poisonous.
It's probably not.
Don't crunch him.
Why are spiders coming off of you? All right, so that track idea is the same thing as this one. So I think in your homework maybe throughout the next couple of days you might see a question that involves running around a track. You can kind of come back to this question and see how we address this one. Basically what's going on here is that we've got, it says a 2-foot wide circular track for a camera dolly is set up for a movie scene. It says the two rails of the track form concentric circles. The radius of the inner circle is 8 feet. How much further does the wheel on the outer rail travel than the wheel on the inner rail? So essentially, this thing's going to go all the way around and come back to where it's at, right? So it travels the circumference of this track, correct? Okay. But this wheel right here, travels a shorter distance than that wheel there, doesn't it? Because the circle that it's on is a smaller circle. So that red wheel is the circumference of the inner track. What is the radius of the inner track? 8. Circumference is 2 pi r, right? So 2 pi times 8 gives me 16 pi. If I do the circumference of the outer, okay, 2 pi r again, right? What's the radius of the outer track? 10. Okay, you go from here all the way out. It's the segment addition, gives me 8 plus this 2. So what's that give me? 20 pi. So now the question was, how much further or farther does this wheel travel? 4 pi. Okay? And we're going to leave it that way. We're going to leave it, we refer to that as in terms of pi. Okay? Whenever they say in terms of as your answer, and they give you like x or y or some symbol, in this case pi, it means that needs to show up in your answer. You don't change it to 3.14, you don't change it to a better decimal on your calculator and you get like 12.56 or something like that. You leave it as 4 times pi. That make sense? All right? And we're going to do that a lot in this next 20 so days, leaving things in terms of pi. All right. Now, what if I only wanted to? What if that dolly doesn't make it all the way around? What if it only makes it halfway around, or 2/3 of the way around? Well, what would I do with the? Let's say let's look at the 16 pi number. If I only go half the way around, what would I take that 16 pi and do with? You would divide it by 2, right? Or multiply by 1/2. What if I wanted to go 2/3 of the way around? This is why I was multiplying instead of dividing. Dividing by 2/3 is kind of a pain in the butt, right? Okay? Or taking 2/3 and trying to figure out what do I need to divide by so it equates to 2/3. If I only want to go 2/3 of the way around, don't I take that 16 pi and multiply it by 2/3? So if I want to go around a portion of my circumference, I multiply by what portion I want to go around, or what fraction of the circle I want to go around. Okay? So what have we called in previous chapters a portion of circumference? Called an arc. Good. Okay. Okay. And right now, what we're going to be able to do, because we know circumference is a length, if I multiply that by some fraction between 0 and 1, it's going to give me a length that is less than my circumference. It's going to be that fraction of my circumference that I'm interested in. Okay? So this formula here where it says length of arc AB, it is equal to the measurement of arc AB. And the measurement of arc AB is going to be as a degree. And you divide that by 360. Because that is going to give you the fraction that this red arc is of my entire circumference, won't it? Let's say that red arc is 60 degrees. Okay? If I take 60 divided by 360, what's that reduced to? 1/6. So it tells me that this red arc is 1/6 all the way around my circumference. A portion of my circumference, right? And if I know what my circumference is, maybe we say this R here just to make things nice for our math. Let's say R is 36. If I take 1/6 times 2 times pi times R, can I now find the length of A to B on that arc? 1/6 times 36 is 6, right? Times 2 pi would be 12 pi. So I'm going to multiply my circumference by some fraction of my circumference, essentially. Okay? And that fraction is always generated by taking your arc measurement divided by the total. Okay? Total number of degrees in a circle. Okay? So, do a couple examples of this. Alright, so I'm looking at that first picture. Actually, let's go. I think I get these steps. There we go. I want to find that red arc up there. Okay? This is where I was saying it's important for us to understand a little bit about chapter 12. They don't tell me what this red arc x to y is, do they? But we should be able to gather that information from other parts of the picture. That central angle is 90 degrees, right? So what is x to y's measurement as a degree? 90 degrees. Central angle is the same as the arc that intersects. Okay? So, if I'm trying to find length of arc xy, you're going to take xy's degree divided by 360, xy's measurement, that arc's measurement as a degree, and then times 2 pi, and then your radius. What's your radius? Okay? Now, what does that tell me? What's 90 divided by 360? Or what's 9 divided by 36? 1/4. Okay. And then multiply that by 2 pi times 8. Do you see how that 90 over 360 tells me the portion, or maybe if you want to think about it as the percent that I'm going to travel around my circle? I'm going to travel around a quarter of the way, or 1/4 of the way around. And if my circumference is 16 pi, right? What's a quarter of 16 pi? 4 pi. Okay? So 4 pi would be the length of x to y. So that means that if I were to take that arc length xy and lay it flat, stretch it out, lay it flat, I would walk a linear distance of 4 pi. Feet, inches, whatever unit, inches in this case. Is that okay? We can deal with major arc lengths as well. Okay? So that's 240. So if I want to find the arc length of x to p to y, x to p to y's length, I'm going to write L of x to p to y. So length of x to p to y. I'm going to take the measurement. What would that measurement be? 240 over 360, and multiply that by 2 times pi times 15. 240 divided by 360 was 24 divided by 36. 12 goes in the both, right? 2/3. 2 pi times 15 is 30 pi, isn't it? What's going to happen with that 3 and that 30? Gives me 10 pi. So total gives me 20 pi, right? 2 times 10. Okay. So that would be that red arc there. Okay. Can I find that black arc? What's that black arc's measurement going to be as a degree?
It's
120, right? Okay. Or, because I already know that this red one is 2/3 of the way around, that black one is 1/3 of the way around, isn't it? Okay, so you can maybe do that, find that percent or portion a little bit quicker that way. Is that something we can do? Okay. All right, so that brings us into this, and I want to discuss this because, and we can do this in the short time that we have, because they're very similar relationships. Okay. Area, you know, to be pi r squared, correct? Area to be pi r squared. Okay. That circle on the bottom here. Okay. It looks like a slice of pizza, right? Or a slice of pie, whatever. Okay. Those types of figures where the vertex is the center of the circle and the sides of the image are radii of the circle, that is referred to as a sector. Okay? Sector of a circle. Would you guys agree that that yellow sector looks like it might be like a quarter or a fourth of the entire area? So do you think I would take my area of my circle and multiply by 1/4 to find the area of that yellow region? Does that make sense? So hopefully maybe that opens your eyes to this formula here, that if I'm trying to find the area of a sector, it's your area of a circle, it's your pi r squared, times then the fraction of the circle that you're interested in. And this here provides me the fraction that that yellow region is of the entire circle. Okay. Again, though, I got to know or have the ability of finding what that arc measurement AB is as a degree. Okay. So we take arc AB divided by 360 and then multiply it by pi r squared. Is that the same kind of principles that we use when we find arc length? Yeah. Okay. We just got to know which of the two we're talking about. We're talking about a length, we're talking about an area, and then apply the same principles. Okay, so they're very, very similar questions that you see. So I'll do an example here. So this one says find the area of this yellow sector down here. Okay, so I'm going to say area of my sector is equal to, okay, we take our arc measurement as a degree. What's our arc measurement here? 72 degrees. And you're divided by 360 degrees. You're then going to multiply that by pi r squared. Okay? And the reason we do that is because this here will tell me, and that reduces to 1/5, basically tells me that there are 5 of these slices that would make up the whole circle, right? I only want the area of one of them, so I take the whole circle and multiply it by 1/5, and it should give me just one of those slices. 15 squared is 225. Which of those three numbers, which two work well together? Yep, I'll multiply those together, and that gives you 45. No. Yeah, it is 45. Okay. 45, and now what do I need to do with that? Multiply by pi. And now my units would be centimeters what? Squared. Okay? And we would leave it that way. Okay? That is leaving our area in terms of pi. See how I write that in those directions? Leave your answer in terms of pi. If you change that to, 45 times pi ends up being 141.37166694, and then at some point I got to cut that off. When I cut that off, when I round that, I don't have the area of that yellow region. I have a very close approximation, depending on how many decimals I use. We want the exact thing, 45 pi. Okay? Is that something we can do? All right, just real quick. When you get to your homework, there's going to be a question that asks, several questions that ask you to find an area that looks like this. Okay? We're call that a segment of a circle. We'll work a little bit on this tomorrow, but there is going to be a question over it. I want you to kind of think about what's going on here. There's not a specific formula other than kind of this relationship between two individual formulas. Do you see that if I take that sector and remove away from it that triangle, I get that segment? Okay? What is that triangle always going to be? What kind of triangle is that? It is always isosceles. So you're going to have to work with your isosceles triangles, altitudes of isosceles triangles, and that kind of stuff to help you generate the area of that segment. Okay? Some questions in your homework in regards to that. Okay? If you remember back to working with pentagons and octagons, we did a question of that when I asked you, because on a worksheet said, like a blue pentagon and a circle surrounded by a circle that's painted red. How much area is red? Found collectively 8 of those things, 8 of those segments. If I want to find one of them, I would divide that sum by 8, right? This is going to target that question a little bit faster. Okay? Work on that assignment, okay? And we'll come back tomorrow sometime.